Thank you for joining our webinar this morning. Today we are going to be presenting a couple of presentations. First, it focuses on modeling faults and discontinuities using zone joints in FLAC3D and IMAT. And we're going to follow that up with a little more, delving a little bit more into zone joints, the logic, and how those can be used in IMAT as well. Our first presenter is Tatiana Katsaga. She is a principal geomechanics engineer and was a consultant with ITASCA for more than 15 years. She has just recently started a new role with Agnical Eagle as a rock mechanics advisor. She has a PhD in civil engineering, and her area of expertise is on the mechanics and numerical simulation of continuum and discrete media. She has provided consulting on many projects, including mining, deep mines, block cave mining, pillar stability, optimization of mining layouts, nuclear waste storage, geothermal energy, and petroleum. She also specializes in geophysical data acquisition, including advanced processing and interpretations. Our second presenter, Dr. Jim Hazard, will be speaking on zone joints. He is a geological engineer with a PhD in geophysics. He has extensive experience in software development for geomechanics and is currently the software manager at ITASCA Consulting Group in Minneapolis, as well as the product manager for 3DEC. Dr. Hazard is also a consultant with ITASCA and has worked on several projects evaluating the stability of open pit and underground mines. Other interests include numerical modeling of seismicity and hydraulic fracture. Dr. Hazard is a registered professional engineer in Ontario. These presentations have been pre-recorded, but both Jim and Tatiana are available online for questions. We will answer any questions you might have at the end of both presentations. If you have a question, please use the Q&A icon at the top of the Teams meeting. Just click on that, type in your question and submit it, and then we will address them at the end. Thank you.
Hello, everyone. Welcome to today's webinar. We will be talking about how to model faults and structures in slope stability or underground models using explicit approach. This webinar is on modeling geological structures like faults and discontinuities using zone joint approach in FLAC3D and IMAT. Our goal is to improve slope stability analysis in mining by making the model more realistic when structures are thin and show discrete movement. The example in this webinar will show how important it is to model faults accurately to get reliable results, especially when analyzing slope failures. Here we show an example using LEO failures that happened at Bingham Canyon Mine in May 2021. We had three main objectives. Build a strong modeling framework within our software, which is FLAC3D and IMAT, to improve performance of slope stability simulations and to compare zone joints with interface approach used in earlier versions of FLAC3D, because we wanted to see which one works better for complex geological conditions. One big challenge we would like to emphasize is modeling faults or bedding planes when they're not straight, when they're bent or intersect each other. It's very tricky, but it's absolutely necessary to get accurate slope stability results. ITASCA combines powerful software and also expert consulting to help with geomechanical decisions. Using FLAC3D, Griddle, IMAT, we can model faults and joints very precisely, even in complex situations. In this work, we use Griddle to represent faults and joints in the mesh realistically. Also, we use FLAC3D and IMAT to model geological structures. This helps to make slope stability assessments more reliable. FLAC3D creates continuum-based models, but can also include explicit faults and structures using zone joints or interfaces. Zone joints were introduced in FLAC3D version 9 as a new way to model these features. Both zone joints and interfaces use the same linear column shear strengths model to simulate how they fail or slip. Zone joints also allow us to include residual strengths, which helps to model post-peak after faults starting to slip. So it helps to capture their behavior more accurately. Here we show a simplified example. And in this simplified example, we are using IMAS to model rock mass, which is based on Hawk-Brown strain softening constitutive model, and we added faults using Griddle. We tested both interfaces and zone joints to see how the model behaves and how long it takes to run. We use the same approach in both interfaces and zone joints to compare. Even we've got very similar results in terms of response of the model. So we show that you can comfortably switch to zone joints if you use interfaces before. In this example, we examined the stability of the block. We are showing displacements as we are varying friction of the faults. The friction of all faults were gradually decreased until the block began to slide. We also compared how long each model took to run. The zone joint model was 28% faster than the interface model, which is a big improvement. Through various projects and examples, we showed that zone joints give very similar results as interfaces, but they run faster and handle complex fault intersections much better. Also, zone joint logic can incorporate residual strength, which was also very important for some of our projects. In May 2021, a slope failure, which is known as Leo failure, happened at Rio Tinto Pencam Canyon mine. Thanks to early detection from monitoring systems, the team was able to safely evacuate people and equipment. ITASCA was brought to analyze the failure and to understand what caused this failure. The goal was to learn from it and to help to identify and prevent similar issues as mining continues. The results gave a very clear picture how rock mass behaved and what caused the failure. This helped to support risk management and guide decisions for future mine expansions. Zone joints are available in IMAT as well. Griddle is required to introduce faults and structures in the mesh. Then the mesh can be imported in IMAT and properties can be assigned to introduce structures and faults. We would like to thank you for your attention. If you would like to learn more about ITASCA software or consulting services, please feel free to reach out or visit our website. Thank you.
This is Jim Hazard. I will now dig into the details of how to model faults and discontinuities in FLAC3D and IMAT. So it is certainly possible to model discontinuities in FLAC3D, even though you may think of FLAC3D as a continuum modeling program. It is possible to model discontinuities, and there are different ways that we do that. So Tatiana touched on this already, but I'll just elaborate a little bit more. There's really two main ways of doing this. Number one is using the ubiquitous joint constitutive model. So you can see here on the left, I have a little conceptual picture of what that might look like. Imagine you have a set of parallel, closely spaced joints. You don't necessarily want to put all of those joints in your model as actual discontinuities. You can assign the ubiquitous joint constitutive model, and the continuum will then behave as if there were a set of parallel joints in there. You specify an orientation and a strength for those joints. And again, the continuum will behave as if the joints were there, but we're not actually putting discontinuities in there. If the movement, for example, separation and shearing on actual discontinuities is important, then you probably want to explicitly put specific discontinuities in the model, especially if you have major faults or other things that have been mapped, and the behavior of those things is important, then it is possible and advisable to put them in as discrete structures within the model. Now, Tatiana talked a little bit about interfaces and zone joints. So these are two very similar things, but there are some subtle differences here. Before FLAC3D version 9, we only had the ability to put in what we call interfaces. These are true discontinuities. So the way that it works is that you identify the faces where you want to have a fault or a joint. You do a separation, right? So you're duplicating the grid points. And this allows there to be movement between the two sides, right? Opening and potentially shearing. But the way that the interfaces work is that they're really one-sided. So what this means is imagine you're sort of painting on this sort of discontinuity onto one side of this split. This is shown in purple here, and on the other side, you know, it doesn't consider itself part of the discontinuity. So all of the calculations, the forces and displacements and so on are calculated on this purple side, and the gray side here is just reacting. This is fine. This works okay. We've done it for years. It just gets a little bit weird when you start considering complicated intersections. You know, because these are one-sided, what is actually happening at these intersections, and which side is the dominant one and which side is not, and so on. Post version 9, we have a new technology which we call zone joints. And what this is it's a true two-sided discontinuity. So again, you identify the faces where you want to slip to occur or separation. You can do a separation, you're duplicating the grid points, same as before. But now what we have is a two-sided joint, so we don't have to identify which side is the interface is on. You know, both sides will interact with each other when they come into contact, and you get a slightly more realistic behavior. And it also makes the the joint intersection behaviors and calculations much more accurate. So post version 9, I would say probably more people are using this zone joint technology and moving away from this older interface technology. Either way, if you're using zone joints or interfaces, or in fact, ubiquitous joints, we assume a Coulomb shear strength criterion. So this is probably familiar to you. The shear strength is dictated by a user-specified cohesion, a user-specified friction angle, and then the normal stress and potentially water pressure. So if you plot, for example, shear stress versus shear displacement, you will see a linear behavior as the shear stress increases according to some user-defined stiffness. Then you reach the shear strength, which is the cohesion plus the normal stress times the tangent of the friction angle, and then this thing will start to slide, right? It is possible to specify a residual cohesion and a residual friction angle, which is different from the peak. And then what that means is that once sliding starts, the joint actually weakens. Okay, so the strength decreases instantaneously, and you will see a new strength, and you know, it will continue to displace in shear at a constant shear stress, and it will just happily slide along there. If I plot instead shear strength versus normal stress, you can see the typical, you know, more Coulomb curve that you're all used to seeing, where at zero normal stress, you have a strength that's determined by the cohesion, and then the strength increases according to the friction angle. And then again, if this strength is exceeded and the thing starts to slide, you can drop down to this residual strength. And often people will set the residual cohesion to be 0, which sort of makes intuitive sense. And often people will set the residual friction angle to be the same as the peak friction angle. So you might see the residual strength curve looks like this. There's also a relation for tensile strength. So you can specify a non-zero tensile strength. And again, it will just open up and the normal force will increase according to some user-specified normal stiffness until that tensile strength is exceeded, and then it essentially breaks, and the normal force goes to 0 by default. Okay, so how do you put the discontinuities into FLAC3D? For ubiquitous joints, it's easy. You just specify an orientation and a strength, a cohesion and a friction, and you just assign that to zones. You don't need to worry about changing the geometries around or anything like that. You just identify a region that's full of ubiquitous joints, and you assign the necessary properties, and it will behave as if there were a parallel joint set there. For the zone joints or the interfaces, it's a little bit more complicated because you need to identify where these discrete features actually are. And so the way it works is you need to identify a set of faces, a set of zone faces, and then you can do a separation operation where the faces are separated and the grid points are duplicated. And again, this allows there to be relative movement between the two sides. For complicated geometries, if you have a bunch of intersecting faults, maybe like in this example here, you will almost certainly need to use Griddle or some other similar software to generate the geometries such that the faces line up with the actual mapped discontinuities. It is also possible to simulate discontinuities in IMAT. Again, you could use ubiquitous joint model. There's no built-in way to actually create true interfaces. Again, you could potentially use Griddle, and I'll show that on the next slide. But one thing you can do within IMAT without leaving the program is create these weak zones. So as you may or may not know, IMAT builds the models using an octree system. And what this means is that, the whole model is composed of little cubes, and you have small cubes in the region of interest, and you have bigger cubes away from the region of interest. And so you can see here, for example, we have an open pit. It does a pretty good job of matching the geometry of this open pit, but it's not perfect. It's not an exact match. And so for modeling a discontinuity or a fault, it's not that easy to have an exact match to the surface of this fault. So what we can do instead is just find all of the zones that are maybe touching this fault or within some distance of the fault and give them a set of weak properties, right? So instead of modeling a true discontinuity, we're just modeling a weak zone here. In some cases, that's great. In some cases, maybe that's not great. If modeling the actual discontinuity itself is important, it's still possible to do this within IMAT, but you just need to generate the geometry first with Griddle. So if you generate the geometry and you have identified faces that line up with certain faults or joints, you can import that into IMAT, and then everything becomes relatively easy, right? You can choose the faults, and then you can assign properties to them, using the IMAT interface. So here I've got a model with just one fault in it, and I can specify friction angle and cohesion and tension limit and so on. Once I've set up my model and properties and so on, I hit run, and the operation of separating and duplicating grid points and assigning properties and all that stuff just happens automatically. And then when it's done calculating, I'm back in IMAT, and I can look at the results within IMAT. So here's the same example. Now I'm just looking at the shear displacement on the fault. Of course, there are other things I can do here, cut planes and isosurfaces and so on. This is just showing you how it's possible to look at results on these discontinuities within IMAT. So that's basically it. I mean, to summarize, if you want to model discontinuities in FLAC3D or IMAT, you can use ubiquitous joint model. You can use interfaces or zone joints. These are very similar. You could also just make a band of weak zones, and that's relatively easy as well. Whichever method you use, we will be assuming a Coulomb shear strength criterion where you specify a cohesion and a friction and possibly a tension strength. If you have relatively simple geometry, like something bedded, maybe a coal mine, it would be possible to just build this in FLAC3D and identify the faces that form the beds and do the separation and so on. If you have more complicated geometries with intersecting faults, most hard rock mines, you would need to create the geometry in Griddle or similar, and then import that into FLAC3D or IMAT. And that's all I have. Thank you for your time.
Great. Thank you, Jim. As I mentioned earlier, we will now take questions and do our best to answer them. I see there are a few people who have asked some questions in the chat, so please feel free to use the chat to post questions or to use the Q&A icon at the top of the Teams meeting dialog, and then you can type them in and submit them. So we have a question that's being answered online, but I'll just read it out if you haven't had a chance to see it in the chat. Were the zone joints trialed on the Bingham failure? And Tatiana responded, yes, we use zone joints to represent the faults that define the failure mechanism. Either for Jim or Tatiana, how can we estimate normal and shear stiffness for joints?
This is Jim. I can take that. There was a fairly extensive section in the documentation about that because we recognize that this is not information that people usually have. So there's kind of rules of thumb. You know, you want to set the normal stiffness such that it prevents overlap. The shear stiffness is a little bit harder to determine, but again, some sort of rule of thumb is usually, you know, maybe 10% of the normal stiffness or 50%. So, you know, I recommend just going and looking at the documentation. There's quite a lot of information about how you might go about estimating these things. In the end, it's kind of not that sensitive to what you choose. You know, the real important thing is the strength and when they start sliding. But, you know, you still need to come up with a number. So, yeah, I would just go and look at the documentation.
Okay. And I would like to add that it can be also a part of calibration because we tried stiffness to include as calibration parameter. In some projects, it was successful.
Great. Thank you both. I'm also just submitting in the chat a link to GeoBot, our AI assistant. GeoBot's being trained on our documentation, our forum. So if people have asked questions and gotten answers, as well as examples. So GeoBot is a really good resource if you have questions like that. Next question. How many zones should be across the fault area? Jim?
Well, maybe that's for Tatiana. I know you have some experience there.
Yes. So it's very important to have a very good resolution for fault volume to be resolved in shear. So we try to use at least 7. And I know sometimes it's difficult, but if you really want to see your zone joint, ubiquitous joints working across the weak zone, we recommend to use 7, 8 across the fault.
I'll just add to that, though, that's definitely true if you're using ubiquitous joints to represent the weak zone. If you're just using more Coulomb, I think it doesn't need to be that thick.
Yes, I agree.
The directionality is not there, right? It just fails in any direction. So I think probably we're using 3 or 4 across if you're using more Coulomb. So.
So if you don't need anisotropy along the fault, you can use just weak fault as more Coulomb, as Jim mentioned. If you would like to include directional deformation, so it's recommended to use ubiquitous joints, and then you need to make sure you have enough resolution.
Right. A question to Tatiana. In your presentation, was it a comparison between zone joints and interfaces, or was it just zone joints?
So in my presentation, we showed examples of projects when we used zone joints, and we also compared with interfaces because in the past we always use interfaces. So before switching to zone joints, we did extensive investigation, how they compared. And we like to investigate before using new tools. So basically our comparison showed zone joints much better performers than interfaces in terms of speed, and they also behaved better at intersections.
Very cool, thank you. Next question. Can you please explain the case where it is good to use weak zones versus zone joints? Is it related to the actual joint structure?
I would say it's related to geology description. If you have a fault zone which is thick and show as a geological representation, it's a weak zone. So it's better to use weak zones, basically. If you see very discrete structure from geological point, which shows evidence of sleeping, then it's highly recommended to use zone joints or interfaces, especially if it's a thin structure.
Thank you. Will zone joints lead to rotation of blocks?
I'll take that one. I think the answer there is sort of. You should be aware that the zone joints only work in small strain, so you're not going to get true separation or rotation in the sense that the contacts are disappearing and new contacts are forming. It's not like a 3-deck model. However, you can still see rotation effects. For example, I've seen people do toppling type problems with parallel zone joints, and you can capture that toppling kind of mechanism. But depending on how far you want to go, it's not a large strain problem, so you're not gonna get things truly rotating and like forming new contacts and stuff like that. So I don't know. The answer is sort of.
But Jim, that is something that we're working towards as well as a large strain zone joint.
Oh yes. Mm-hmm.
Yeah. Thank you. Next question: have we considered ever implementing the Barden-Bandis approach for joint strength in zone joints?
That's a good question. We definitely considered it. The problem with Barden-Bandis is that it's only ever been formulated in 2D. So if you know about Barden-Bandis, there's all kinds of things about how things slide and then reverse and slide backwards. There's no formulation about what happens if they start sliding and then change direction and slide sideways. So doing it in 3D is basically a research project that we have not undertaken. However, we could totally implement that in 2D, and it's actually a good idea. We should do that. And I mean, it's certainly possible to do it in 3D, but it would be, like I say, a research project. It's not currently defined, so it's just not something we've done. So
sounds like a good PhD topic if anybody's looking
for
a
subject. Something like that, right?
Thanks, Jim. Question: should we use larger strain or small strain? But I'm not sure what that refers to exactly. Ravi, if you could expand on that, I'll come back to that. If we have a DFN model where some fractures are very close to each other, would the zone joint logic work to support that?
Theoretically, yes. The challenge would be creating the model itself. But I have seen people do it in Rhino and Griddle. They have a DFN and then they create the mesh and build the model. So yeah, it's certainly possible. The zone joints can handle it. The challenge would be to actually make the model. So
in terms of the zoning between such
right
closely spaced faults.
Right.
And also you will need to take special care of separation of the faces, especially if you have full fractures on both sides from the same zone.
Right.
Mm. And I think 3-deck, correct me if I'm wrong, Jim, actually has rules that you can implement that if you have very closely spaced faults, it'll actually kind of average it out to a single one to simplify the meshing.
Well, the DFN logic in general has some like collapse functionality and things like that. So yeah, what I would do is, make the DFN and then collapse it down if they're very close together before you even try to make the model, because that's when you get yourself into trouble, is when they're very close together and almost parallel. So
Okay, clarification on the previous question about small and large strain. Should we use large strain or small strain when we are using weak zones to see the shearing across the joint structure for Bingham scale model, for example?
For large scale models, we are not using large strain mode just because having so many structures, almost impossible in real life projects. So we are always using small strain mode. And now specifically, zone joints are not available for large strain. But
Right.
even if they would be available, I would avoid using large strain for very complicated geometries of the faults.
Tatiana, in the Bingham model, how many faults were there approximately?
I believe we had around, in the latest model, we had around 70, 75, something like this.
Yeah. Okay. I'm seeing some questions on the Q&A section. Is zone joint equivalent to double interface, one interface on each side of the two surfaces in contact?
Sort of. There's a node contacting a node with the zone joints, whereas with the interfaces, what you really have is a node contacting a face on the other side. So it's not exactly correct to say that it's an interface on both sides. It's just kind of a different technology. It's sort of a node contact rather than a node face contact, if that makes sense.
And that's similar to a 3-deck UDEC logic, correct?
Yeah, the whole point of the zone joints was to try and make it more similar to 3-deck. And it's theoretically more accurate than the interfaces, but it's also easier to actually build the models because you can say just separate and install zone joints on all these faces and it sort of magically works. Whereas with the interfaces, it's much more challenging because you have to figure out which side you're going to put things on. You know what I mean? So, yeah, it's just easier and better.
And also it's behaving more physically logical, dealing with interfaces.
You mean than interfaces?
Than interfaces, yes. Basically, zone joints on intersections are much more physically logical than interfaces. Sorry.
Thank you. Okay. Does anyone else have any questions? I guess one thing I just would like to point out, when Jim showed the example of a FLAC3D grid that was imported into IMAT, which is ITASCA's mining analysis toolbox, which is a kind of pre-processor, post-processor for FLAC3D for large-scale underground or surface mining problems. Of course, it was a pretty simple fault from an example. So it had, if you wanted to represent that with ubiquitous joints, you could specify one set of orientations for those weakness planes. But if you have a more kind of undulating fault or faults, and you wanted to assign ubiquitous joints to them, you can imagine that there's a variation of those orientations. So there's actually a little checkbox in IMAT that will look at the normals of all the facets of the surface representing the fault, and it will automatically align the ubiquitous joints to contour, follow that undulation. Jim, question. Will IMAT at some point be able to handle the meshing without resorting to Griddle?
Yeah, that's the dream. It's quite challenging to do that, and we have been working on it. We haven't got it working yet, but yeah, hopefully that's the dream anyway.
So we're doing some research into that presently. Okay. Any other questions or comments? We will post a recording of the webinar, including the Q&A session, online to our YouTube channel later today. Anyone who's registered for the webinar will get an email with a link to that shortly thereafter. If you're interested in setting up a discovery call to learn more about any ITASCA software, I included a link to our bookings calendar at the top of the towards the top of the chat. And if you're interested in a free 2-week trial, please just set up a discovery call and we can work with you on that. Well, I'm not seeing any other questions. So Tatiana, thank you very much for joining us today. Wish you all the best in your new career. And Jim, thank you for joining. Thank you everybody for attending today. If you have any other questions, just send us an email at sales@itascasoftware.com and we will follow up. Thank you everyone. Have a good day. Bye-bye.
Thank you. Bye.